Hello, everyone, and welcome back. In the previous two videos, we introduced improper integrals. And we saw that to take care of these integrals, we have to introduce limits. We think of these integrals as being the limits of definite integrals over either a finite range of the domain, or as we are approaching some singularity in our integrand. Now, there are a number of functions that we don't have direct access to. They're antiderivatives. An example of that might be e to the minus x squared, for example. We don't have an explicit description in terms of elementary functions what its antiderivative is. So the question arises, if I take an integral of e to the minus x squared over an infinite domain, does it converge? Can we say that this is going to be finite? Because if it's finite, then we have access to it at least numerically. We can program a computer in order to approximate it using something like Simpson's method. So this is what I want to talk about today. I want to talk about the different tests that we can run to say whether or not an integral converges with or without knowing what its exact value that it converges to will be. And let's start with exactly that function that I was just talking about, that function e to the minus x squared. So let's start with an example. Let's say, does the integral from 1 to infinity of e to the minus x squared dx converge? Well, this thing is a positive function, right? So we're really asking ourselves, is there a finite amount of area contained between 1 and infinity underneath the curve e to the minus x squared? Now, we also know that properly, this thing should be written as a limit. It should be the limit as b goes to infinity, the integral from 1 to b e to the minus x squared dx. Now, just like I said, we do not have access to what the antiderivative of this is. And this is not something I'm just withholding from you that we're going to learn later, right? This is a function that's widely used throughout mathematics that we don't have an explicit description of its antiderivative. So the question is, how can we check? Is this thing finite or not? Well, we can do some comparisons with functions that we can work with. So for example, for x greater than or equal to 1, we know that if you square a number, that is bigger than a number itself. And this only works if you're bigger than 1. 2 squared is 4, 3 squared is 9. If you're smaller than 1, this doesn't work, right? 1/2 squared is a quarter, which is smaller. So it's only going to work when x is bigger than 1. Now, if I multiply these things by a negative, I reverse the inequality here. And the exponential function preserves orders. So I can raise both sides to e, and I get that e to the minus x is greater than or equal to e to the minus x squared for all x greater than or equal to 1. Okay, so that tells me that the area underneath the curve of e to the minus x squared has to be less than or equal to the area underneath the curve of e to the minus x, because e to the minus x is above it. So this tells me that the area between 1 and b, where b is larger than 1, for this has to be less than or equal to this. Again, read that as an English sentence. The area underneath the curve e to the minus x squared between 1 and b is smaller than or equal to the area underneath the curve of e to the minus x between 1 and b. But now this is an easy integral. You can compute this fairly easily. You get minus e to the minus b plus e to the minus 1. So I took the liberty of just skipping a couple steps in the middle. I think it's getting a little monotonous. So also, you know that you're subtracting off something positive here. So e to the minus b is a negative number. And that means that this thing is smaller than e to the minus 1, which is something like 0.36788. Now that thing's finite. We also know that this thing is positive. This original integral right here is positive because it's above the x-axis. So that tells me that, therefore, this integral converges. Why? Well, the limit as b goes to, we can use the squeeze theorem here, right? The limit as b goes to infinity of 1 to b of e to the minus x squared is less than e to the minus 1. That's just using the squeeze theorem from what we did on the right-hand side. So not only do we know it's finite, but we've narrowed down where the value of this integral actually is. It's somewhere between 0 and 0.36788, whatever that happens to be. And you can use this throughout your work in order to determine whether or not an integral, one of these improper integrals of type 1, is going to converge or not. So let me give you a result here. This is a theorem, and this is what's called the direct comparison test. So it's a comparison test because it's allowing us to compare two functions together to see, if we understand one of them, then we can use it to understand the other one as well. So let's let f and g be continuous on a to infinity, with 0 less than or equal to f of x, which is less than or equal to g of x, for all x greater than or equal to a. So if you want to put this in the context of the previous example, f of x would be e to the minus x squared, g of x would be e to the minus x. So then we have two ways of comparing. If the integral of g of x converges, then just like the previous example, this tells us that the integral of f of x converges because we get an upper bound and the squeeze theorem tells us that the limit exists. Now you can do this the other way too, and you can use f of x to push up g of x to show that g of x might diverge. So you can also say, if the integral of f of x diverges, then the integral of g of x diverges too. And again, this is just sort of a little, almost kind of like a squeeze theorem type result, because f of x is below g of x. So f of x is going to infinity. That's pushing g of x to infinity with it. Okay, let me illustrate this with just a bunch of examples, because it's one thing to just read this result, and I know that it's a little hard to get your head around sometimes. Let's look at some examples where we can use this. So example 1. We can say this integral. So we're going to write if it converges or diverges. Okay, well, I'm going to write if it converges or diverges in red off to the right here, but let's do the comparison underneath. The first thing is, this thing is positive because I've got a sine squared and an x squared. And also, sine squared is between 0 and 1, which tells me this thing is no bigger than 1 over x squared for all x greater than or equal to 1. Also, from the work that we did 2 videos ago, we know that this integral converges. So set f of x equal to sine squared x over x squared, and g of x equal to 1 over x squared, and use the theorem and use the comparison test, the direct comparison test. So we see that G dominates F. It's bigger than or equal to F everywhere. And G converges. That means that this integral converges to. I have no idea what that converges to. That I do not have an integral technique that's going to help you solve that thing. But at least we know it's not infinite, right? That's a good thing. We've at least narrowed some stuff down. And in fact, it can't be any bigger than whatever the integral from 1 to infinity of 1 over x squared is. Okay, let me give you another one. So here's another ugly integral. The integral from 1 to infinity of 1 over the square root of x squared minus 0.1 dx. Does this thing converge or diverge? Okay, well, first of all, we know that this thing, this is greater than or equal to 1 over the square root of x squared. And that's because the denominator in this case is going to be slightly smaller, making the fraction bigger. That's because it's smaller because I'm subtracting off the 0.1. But in the region where x is greater than or equal to 1, this thing is just 1 over x. So on x greater than or equal to 1. Let's say 4. That seems like odd language. And we already showed 2 videos ago the integral from 1 to infinity of 1 over x dx diverges. So set f of x equal to 1 over x and g of x equal to 1 over the square root of x squared minus 0.1. Sorry, I had to squeeze that in there. But f of x is smaller than or equal to g of x. F of x is pushing us up to infinity, and that tells us that g of x is being pushed to infinity with us. So this diverges. Okay, so basically you want to try and identify a function that you know how it works to compare to. Let's try another one. Now, this one is not going to fall exactly into what our comparison test just had, but it works exactly the same way. So we have finite bounds of integration, except now we have cos of x divided by the square root of x dx. Okay, so I have finite bounds of integration. So it's technically, you might give me a little bit of trouble over this. It's technically not exactly the same as the theorem, but the principle remains. You can do this for type 2 integrals. I just don't want to burden you with having to write down what it would be. You would just write a to b instead of taking b equal to infinity in this theorem. So basically, we need to find something to compare cos of x over the square root of x to. Okay, well, the first thing I'm going to tell you is for 0 less than or equal to x, which is less than pi over 2, we have that cosine is between 0 and 1. Right, so this is pretty well known. And so this means we can divide all 3 sides by the square root of x. So I get my function in the middle here. And we know, and the integral from 0 to pi over 2 of 1 over the square root of x dx, well, in this case, this is the limit as a goes to 0 from the right of the integral from a to pi over 2. I'll write this as x to the minus 1/2 dx. Okay, so in this case, this is the limit as a goes to 0 from the right of the square root 2 root x, sorry. from a to pi over 2. We can see that the lower limit is going to disappear. The upper limit is going to be the square root, 2 times the square root of pi over 2. Now, this is going to give us, after taking the limits, I'm going to skip this step. You can see I'm running out of room, but you're smart. You're following. I know that you can do that limit yourself. So you get 2 square root of pi over 2, which if you want to write this, you want to cancel out some 2's there, you get the square root of 2 pi. But the point is, this is clearly finite. So the comparison test says that this is less than or equal to the integral from 0 to pi over 2 of 1 over root x dx, which is equal to root 2 pi. So now we can see we get that this converges. Right, so the same thing works if you use improper integrals of type 1 or type 2. It doesn't matter. All right, so let's take a look at another way of comparing these things. What you could do instead is you could use that asymptotic work that we did a few videos ago, and you can use big O notation in order to determine if these things converge or not. So let's talk about another theorem. And this one says, or this one's called the limit comparison test. And so here, what we'll say, if the positive functions, so we're always going to be using positive functions for this, so that we can't escape to minus infinity, right? So we always have a lower bound of 0. So we're interpreting these things as proper areas under curves. And then we want to put an upper bound on these things that's not necessarily infinity. So if these are continuous on the interval a to infinity, and if they are the same in the big O notation, so the limit as x goes to infinity of f of x over g of x is equal to some limit L, with L being, of course, finite. Okay, so that means f is equal to big O of g, or g is equal to big O of f. Then the integrals a to infinity of f of x dx and a to infinity of g of x dx, either, let's put it in red so it's emphasized, either both converge or diverge, or both diverge. So they have the same behavior. They could be wildly different looking functions, but the point is, if they have the same sort of asymptotics, if they have the same big O, if f is equal to big O of g, g is equal to big O of f, then their integrals are either both finite or they're both infinite. Okay, let me show you an example. Let's go back to one that we already looked at. We know that, okay, let's say show that the integral from 1 to infinity of dx over 1 plus x squared converges by comparing it to the integral from 1 to infinity of 1 over x squared dx. Find and compare the two values. Okay, well, in this case, we're going to have, say, f of x is equal to 1 over 1 plus x squared. So set f of x equal to 1 over 1 plus x squared, and g of x equal to 1 over x squared. So the first thing that we need to do is we need to state that these things are positive on the domain of integration. Of course, this is true. So both are positive on x greater than or equal to 1. So that's good, right? We can still evoke this limit comparison test theorem because we need these things to be positive. They're both continuous. They don't have any vertical asymptotes. They're singular, or they're non-singular as long as x is bigger than 1. And also, we're going to compare them. So we remember how to do this. We remember it usually takes a L'Hopital's rule. So here we go. Let's start writing in pieces to evaluate this limit here. So I get 1 over 1 plus x squared divided by 1 over x squared. We can rearrange this integral for ourselves. And in this case, I get limit as x goes to infinity of x squared over 1 plus x squared. And now what I can do is I can factor out an x squared term from everything. So you actually don't need to use L'Hopital's rule here if you don't want to, but you get a 1 and then 1 over x squared plus 1. So what I did is I factored an x squared out of every term. I canceled them on top and bottom. So if you'd like, maybe I got overzealous there. So this would look like this first. That would be your first step. And then you can say, okay, these cancel each other. This leaves me with the limit as x goes to infinity of 1 over x squared plus 1. Now, taking x to infinity, this piece down here disappears, leaving me with 1. So these things are comparable, right? They in f is equal to big O of g, for example, right? They have the same behavior asymptotically as x gets large. Then also, so from the, what did we call this? The limit comparison test. Since the integral from 1 to infinity of 1 over x squared dx converges, so does the integral from 1 to infinity of 1 over 1 plus x squared dx as well. But just because they converge, that doesn't tell us what the values are, right? I want you to really keep this in mind. This doesn't tell us anything about what the value of these integrals are, right? So if you do this, actually this falls into one of the examples that we did 2 videos ago with p equal to 2. So maybe I'll just put a little note. This is 1 over x to the p with p equal to 2. And we saw that the result of that is equal to 1 over p minus 1. So 1 over 2 minus 1, which is equal to 1. So this example was done 2 videos ago with the type 1 improper integrals. And the integral from 1 to infinity of dx over 1 plus x squared. This one, we have to do a little bit more work. This is b goes to infinity, 1, sorry, to b, dx over 1 plus x squared. This is an arctangent, a tan inverse. So we have tan inverse of x running from 1 to b, which gives me the limit as b goes to infinity of tan inverse of b minus tan inverse of 1. Only one of those terms depends on b. Taking the forward limit of tan inverse, we did this 2 videos ago. This is equal to pi over 2. And tan inverse is equal to 1. Or sorry, tan is equal to 1 when the angle is equal to pi over 4. So equivalently, that means tan inverse of 1 is equal to pi over 4. So this gives me a value of pi over 4. This thing is slightly less than 1, right? It's somewhere around 0.75. If you think of 3 being close, or sorry, pi being close to 3, this fraction is very close to 3/4. So you can see that just because you can compare these two things, and I can give you an answer and say, okay, that thing, you know, I know one of them converges, that tells me the other one converges. It still doesn't tell you anything about the value. That's the most annoying part about this. If you think about the first theorem that I gave, the direct comparison test, this one is much better because it gives you a bound on what your value of your integral of f of x will be. If you know g of x converges and you can compute it exactly, it tells you the integral of f of x is between 0 and whatever the integral of g of x is. Okay, let's do one last example with the limit comparison test theorem. So here's our final one for the video. In this case, let's ask ourselves, so does the integral from 1 to infinity of 1 minus e to the minus x over x dx converge? Okay, so we're going to use the limit comparison test. And in fact, I'm going to let f of x equal to 1 minus e to the minus x over x. And I'm going to compare this to 1 over x. Now, there's certainly an art in being able to figure out what to compare things to. If I scribble down here what my thought process would be, I would say, okay, this thing's like 1 over x minus e to the minus x over x. So what I know here is that 1 over x goes to 0. So does e to the minus x over x. So it tells me this term on the back end is getting small pretty fast, right? The e to the minus x sinks it, and so does the 1 over x. So if x is super large, this piece that I have circled should probably be disappearing fast. And I should start looking just like a 1 over x function. So that's my thought process here. It's not trivial. You know, it takes a lot of practice to get good at comparing these functions. Now, we can't use the direct comparison test because we don't know f of x is less than or equal to g of x, or g of x is less than or equal to f of x. But let's investigate some limits. Let's see what's big O of each other. So let's do f of x over g of x. Now I get the limit as x goes to infinity of 1 minus e to the minus x over x, that's over the whole thing, divided by 1 over x. And so in this case, I get the limit as x goes to infinity. And in here now, you're going to have your 1 over x's canceling, because you can write this as 1 minus e to the minus x over x, and then invert and multiply. So I'm inverting g, and you can see these two guys cancel each other off. And so I get the limit as x goes to infinity of 1 minus e to the minus x. The e to the minus x term disappears, and I'm left with 1. Okay, that's good. But here's the bad news. We know that this thing diverges. So again, why? Well, we know that the integral from 1 to infinity of 1 over x to the p dx diverges for all p less than or equal to 1. Right? We proved that 2 videos ago. So therefore, our integral that we were interested in, 1 minus e to the minus x over x dx diverges. 2. Okay, so what we've seen today is a method of just a yes or no binary answering of questions. Does my function, or does my integral converge or not? It does not explicitly answer what you converge to, but it can help you set up, say, a computer program that can approximate the value as long as you know it's finite, right? So this is sort of more akin to what upper level mathematics starts to become, because we can't get exact answers over and over to problems. But what we can do is we can say, okay, a solution exists. This integral has to be finite. Now let me employ a computer to try and approximate what that's going to be. And the way you can approximate these things is using some of those discretization techniques or those numerical integration techniques, such as maybe the trapezoidal rule or Simpson's rule.